Hi, Rajesh.
Hello, how are you doing?
How are you?
Yeah, thank you for the slides. I copy pasted those slides to mine. Like,
The presentation. Okay.
yeah, I think you use the same format, so it was easy for me to.
Yes, yes. We are participating in another group, so I had the template.
Nice. Okay, we have enough people to start. Morning, everyone, and good afternoon and good evening to the East Coast. Oh.
Yeah, thank you. Good evening.
Uh, yeah, so finally, this has become my initial draft. I think we discussed about this last, our last meeting. Um, so since then, uh, I, I added these two slides from Lila and radar versus sidecar. Like there is one more slide that's been added under 5% approach, cooling power consumption and airflow usage. Um, uh, these results look at least like for a good conversation. Uh, but in terms of the design criteria, I'm I still want to see what could we add in the for the next final presentation. Um, with respect to the draft paper, the draft points, especially like this is like very high level design in terms of okay, what should be there. And I think we still need to jump into a little bit more details in terms of uh, some of these design criteria that were presented here, um, and also add some more details in terms of maintenance versus uh, feasibility. Those are the two things that I still want some feedback from you folks to what could we add into the presentation in those areas. And I think this is 6 slides-ish. So it's not much of a content to talk for. 10 to 15 minutes. Do we usually design the performance metrics like the hardware should supply a particular temperature or airflow rate? Will that be defined by OCP, or is it usually left out? Hey, John.
Hey, Rajesh. I guess I joined the wrong call previously. Yeah. Anyway.
Okay, no worries. Yeah, so I'm trying to see what more details could be added here to make it more effective and also more informative. Um, so as a part of that, what are the details that we can add in the performance metrics or our design criteria in terms of um, liquid supply temperature, airflow, so on and so forth. Um, Usually those are those defined here or not? Okay, in terms of performance metrics that we discussed earlier, um, like do we indicate ranges for this performance metrics to indicate what is the best performance versus what is the recommended performance?
I guess the question is, what purpose does it serve, right? I mean, is it like these are the parameters you want to define so that people who are interested in adopting the technology can make an informed decision, right?
Yeah, they can make their own decision, but in order for them to decide what is more efficient, um, should we should we provide a range in terms of, okay, hey, this is the ranges that at which it's this device is gonna do perform better or like efficiently.
So you mean basically a difference between uh, rated, I guess, uh, performance metrics at the rated capacity versus performance metrics at a, I don't know, expected load or use case? Is that what you're trying to get at?
Um, so while designing itself, like if, for example, if it is designed for approach of, let's say, 25 or 35 is different from when the approach is 10. Would that make sense, or do we
It
are
depends
not?
on the application, Rajesh. I mean, as you know,
Yeah.
if you're using it for let's say GPUs, then you probably want a more aggressive approach temperature. But if you're using it for, let's say, compute, right, like CPUs, then maybe the approach temperature can be more relaxed. So I think if you want to define a range within which the technology would be, let's call it viable or useful, I would say the most aggressive would be a 5 degrees. And then at the upper end, maybe, I don't know, 15 degrees. I don't know, Juan or the others, what do y'all think?
I think the max cooling power is probably more interesting than the performance behavior of a sidecar in itself. Because I think one of the selling things on this is that you could provide more cooling with a sidecar than you can with a rear door heat exchanger.
They are interrelated in a sense. If you define approach temperature and airflow rate, um, usually the maximum and minimum cooling power of the sidecar is also kind of like you can derive it.
Right, but if you were trying to compare a rear door heat exchanger to a sidecar, and you're at the upper limits of what a rear door heat exchanger could possibly cool, then fiddling with the approach temperature gets you potentially a little more cooling capacity out of that. But I think if somebody's going to this presentation, they would be kind of interested in why you would want a sidecar versus why you would want a rear door heat exchanger. And to me, the big difference between the two for a hybrid cooling system is just cooling capacity. That you can get a bigger heat exchanger in a sidecar than you can in a rear door. So to me, I think that you should be really pushing that the approach temperature and capability and efficiency and everything between a rear door heat exchanger and a sidecar is virtually identical. The only thing that you've got is a bigger heat exchanger, so you get more cooling out of a sidecar.
Okay. In my experience, like I have seen from 25 to 75, could be the range in a single rack unit sidecar. Like because we are defining like when I define like sidecar could be any of these things, like multiple use ways of cooling a rack with the sidecar. Now, in a single rack form factor, this is what I have seen. Like, is is there any feedback other than this? That
Yeah, we do one that's 100 kilowatts,
100? Okay.
but it's slightly wider than a standard rack.
Yeah,
Oh,
I think that's where what you consider a rack is like starting to get so gray.
uh,
I think Rajesh, it might be good to define um, because in for liquid to air, I would assume um, the most critical dimensions are the width and the height. Depth, maybe you can probably fit a deeper heat exchanger, but it's a diminishing returns, right? Beyond, maybe 5 or 6 rows of tubes or something like that. Maybe Juan Carlos can comment on that, but um, maybe you define it as a standard EIA 310 rack or something like that. or you use the OCP standard, which is ORV3 or something like that. Yeah.
But I'll go back to the marketing side of this. If this is supposed to be a presentation on sidecars, we're selling sidecars. We're not selling something that's slightly different than a rear door heat exchanger. And to me, the big push for why you would do a sidecar versus a rear door is cooling capacity. And from a marketing perspective, I think you would want to see cooling capacity numbers that are significantly larger than what you could do with a rear door heat exchanger, and push the fact that if you're hitting the upper bounds of cooling for a rear door heat exchanger, here's another technology. Yes, it will take aisle space, but here's another technology that's not significantly different than your hybrid cooling system for a rear door heat exchanger, but you get significantly more cooling capacity out of it.
I think this is right, that the sidecar is able to deploy more power than the rear door, but the biggest issue will be, from my point of view, that the liquid cooled servers are prepared to be cooled by liquid, not by air. So if you use a rear door and you want to move a lot of air through the servers, which are prepared for liquid cooling, not for air, to cool down by air, then you have to move a lot of air through the servers to be able to cool down the water in the rear door. It is a big problem. It is a really big problem, because this equipment are thinking to be cooled by water, not by air. So there is not a space to move the air through the servers.
Right.
So
that's my point right there, is that there's an upper bound on the maximum cooling capacity that you can get with a rear door heat exchanger because of a lot of factors. The size of the heat exchanger, and you're saying that the volume of air that you can effectively get through the server is going to be a limit. Right. So I think the comparison should be, what's the upper bound that you could conceivably have on a rear door heat exchanger? Say it's arbitrarily 40 kilowatts or something like that. And if you've got, if you want to go bigger than that, then you either have to get access to facility water, and we're assuming you don't have access to facility cooling water. So the only other solution, if you're going to stay a hybrid cooling, is to go to a sidecar, because you don't want to require the extra air going through the servers, and you need a bigger heat exchanger.
Yeah.
So I think the sell on this is that this is a logical extension of a hybrid rear door heat exchanger, that the cooling requirements will continue to increase forever. And this is the logical extension of rear door heat exchangers.
Yeah, but this is not a hybrid, it is the air assisted rear door. You mean the air assisted? Yeah.
A hybrid rear door versus a sidecar, to me, are the same.
Yeah, I think radar have, I think, multiple different, I think there are 3 different flavors or versions where you can do, but I think sidecars serves only one purpose. That is,
there is 2 purposes for the sidecars. You can cool the air by the sidecar, like the traditional rear door. It is also possible.
Yeah.
But in either case, if you are using facility water to cool air in the computer room, then a sidecar has more cooling capacity than a rear door heat exchanger does. And I think that's the big market push that we should have on this, is that you get a bigger heat exchanger, you have more either air cooling capacity or water cooling capacity, whatever you need.
Yeah, but take more space. In that case, like always, have pros and cons. But yes, you have more space to put a bigger heat exchanger and be able to move more air, more power, and so on. Yeah.
But I think the comparison should be, what's the upper bound on what you can cool for a rear door heat exchanger, and what's the, I guess conceivably there's no upper bound on where you could go with the sidecar if you took a whole aisle. but there's some practical limitations on
Yeah.
that. So if you've got a rack of IT equipment and you're cooling 40 kilowatts and you've got plenty of airflow, then a rear door heat exchanger would probably work just fine. But the next generation of equipment, if you need 75 or 100 kilowatts in your rack, a rear door heat exchanger won't work. You need some other technology, and this is that technology.
Yeah.
Can we say something like this, like per rack footprint, like this could be the power range. It's
That might actually be a good thing. So if we could, do a kind of a market survey and find out what the average cooling capacity is for a single cabinet wide sidecar, then you could put that as the minimum for what a sidecar would do, and then you could say that the capacity can there are products already on the market that increase the cooling capacity beyond this number by making the sidecar 1.5 or 2 cabinets wide.
yeah, because usually in a when you're converting this air cooled data centers into a liquid cooled hardware data centers, as the power densities grow up steeply, you have space, but you don't have power infrastructure to cool either, or you don't have enough air, or you have multiple limitations that comes with converting those, right? So in that scenario, you can put multiple liquid cooling racks, sidecars. But IT rack could be one. Like one IT rack might have to be cooled by one or multiple of them based on the density and the requirements of approach temperature, so on and so forth. That's what I'm trying to, like convey here. And also capture appropriately based on that. Like you can have a single big sidecar that can then cool like maybe multiple IT racks.
But maybe on this particular image here, you could put some numbers in. So you could talk to some of the manufacturers and find out for your single rack one there, what's a typical cooling capacity. And then the multiple rack would be 2 times that. And then the wide one down at the bottom there would be some very large number.
Yeah, that's this. I think we need someone who is doing that or who plans to do that to answer this. I think this is right now out of the bound scenario, but these two can be defined. That's where I'm coming from with this number saying 25 to 100 kilowatts per rack footprint is the number that I got from at least my experience and then your feedback.
How much you say? 100 kilowatts?
I think 100 kilowatt, Michael was saying that like they have a rack that can do 100 kilowatt.
But it's slightly wider than a standard rack.
Yeah, okay.
So it's kind of halfway between your single rack and multiple racks.
Okay. Juan, in your experience, do you see this be close to 75 or 100?
Yeah, depends of the approach. If you have a very large approach, you will have more. Also, this
Yeah.
number, yeah, if you take only the power, make no sense to put something there because you can have 1 megawatt if you have a delta T of 1,000 grads. I think it's more properly to say by 10 degrees approach, I don't know, 60 kilowatts or something like that. This is more properly.
I see. Yeah, that's why I'm giving a range here in terms of the cooling efficiencies and also the chip temperatures.
I think it is something between per rack. I mean sidecar, something between 40 and 70 kilowatts per rack per 10 Kelvin approach will be something normal.
I see. 10, yeah, 10,
But
10.
like I say, it depends, because if you have a very, very short approach, it is more difficult to get this power per kilowatt. If you have a very large approach, it's more easy because you can play with the flow rate.
Yeah, I think in
Okay,
that case, I think this for this approach and this power makes sense to me. You're saying 10 degrees approach can do is 60 to 70.
40 to 70, yeah.
Yeah, so then the 15 can do close to 100.
Yeah.
But I would put those numbers down by your boxes there showing single racks, so you could say that the cooling range is 25 to 100 kilowatts or 25 to 70 or something for a single wide, with an approach temperature varying from 5 to 10 or 10 to 15 or something like that on there. So somebody could look at that and say that's way more than. Actually, what you might want to do is put a rear door heat exchanger in there.
Rear door also, okay.
Yeah, up above this, and in the same picture, and put the same approach temperatures, and then put what the the cooling capacity is for that. Be the middle one. Yeah, the air assisted in the middle.
This one, okay, gotcha.
Right. But you could do the same kind of picture that's that you've got for the sidecar, but move the sidecar around behind it to show it like a rear door heat exchanger, and then put same approach temperature for comparison that you would have for the sidecar, and then put what the upper bounds are for the cooling. So somebody could look at this in your presentation and say, okay, for a given approach temperature, I'm limited to so many kilowatts for a rear door. I need more than that because I'm filling it full of NVIDIA GPUs. So the only alternative for me is to go to a sidecar.
I see.
And then if they say that I've got 125 kilowatts of cooling requirement on there, then they can see what the upper bound is for a single wide sidecar, and they can say, okay, I can't get there with a single wide, but I could get there with more than a single wide sidecar, either multiple sidecars or a wider sidecar. But I think having the same approach temperature range on all of these diagrams and a range of cooling capacities for all of these diagrams would make it really easy for somebody to look at this and see where they need to be.
Okay, so this would be a sidecar solution, and then like I can add something like uh, an arrow here and then put the numbers.
No, you could just put a text box there and say, for an approach temperature range of 10 to 15 or 5 to 15 or whatever you want there, put a range of what the cooling capacity would be. And when you're doing your presentation, we're selling against another technology. So you would want to talk about the limitations of the other technology and why this technology exists. And like Juan Carlos was saying there, that the amount of air that you can get through the IT gear on there is a limiting factor to how much cooling capacity you can have for a rear door heat exchanger. So there's a solid upper bound for just how high a cooling capacity you can get for this. And the more liquid cooling you go in the IT gear, the less air you've got through the server, so the less cooling capacity you actually get.
Gotcha.
So there's a physical upper limit to how high you can get for cooling capacity for this. And if you need more than that, then this is the technology you have to go to.
But for that, like, that's the transition. I was also trying to see if we can do boundary conditions for this, such as I was saying.
Right. So you would use the same approach temperatures for all of these diagrams that are on here.
Oh, same approach. Okay.
So pick some numbers.
I think then I would need definitely Juan's help in terms of approach and because for a certain approach, usually the powers are within plus or minus 5K-ish to it depends upon the airflow for sure, but usually are very close.
But we could find some typical numbers on this for approach temperatures and then the resulting cooling capacity based on those approach temperatures. And that's going to have some practical upper limit for what a rear door heat exchanger can do.
Okay, approach could be close to 10 degrees C.
And then the resulting cooling capacity would be so many kilowatts.
Oh,
And Juan Carlos can put a number in there.
well,
For the rear door,
yeah.
so as air assisted,
Yes, for the air assisted.
Also, I think 40 kilowatts is possible if we compare with the, if also 30% less capacity than the sidecar.
Right.
Assuming that it is possible to move there through the equipment. But there is something more to consider because usually the servers are not fully liquid cooled.
Right.
So the approach temperature, you want to compare the temperature before the server to the temperature of the water. But in case of the rear door, the temperature of the air is increasing a little bit, maybe 3-5 Kelvin, because you have to cool down the servers as well.
Yep.
So in that case, yeah, you can compare with approach the heat exchanger, but in the real life, the customer will say, yeah, with an approach of 10 Kelvin in the sidecar, I have to take care an approach of 13 Kelvin or 15 Kelvin with a rear door because we have to add this 5 Kelvin or 3 Kelvin. The temperature of the air is increasing by the servers.
Right.
So therefore, it's difficult to compare these two technologies in that way. But yeah, I think for the rear door, if you consider only the temperature before the rear door and the temperature of the water, the power capacity could be 40-45 kilowatts.
Yep. So just think so put a number in there. Say 40 kilowatts is fine. And now,
I'm
and
gonna
now
give you a range, so
that's
it's
fine.
yeah, 35 kilowatts to 45 kilowatts.
That's fine. Now you can just copy this block and put it down by sidecar and leave the approach temperature the same, and put a larger number in for the cooling capacity for the sidecar.
Mm.
I would leave the approach temperature the same, so it's an easy comparison. But now the cooling capacity numbers should be significantly larger.
Yeah, for
Yeah.
10 degrees, I think the approach, I think this would be, he said around 50.
Yeah, maybe more, 50 to 60 or something like that. I don't know, depend of the how much you want to invest in fan power. But something normal,
Tha-
something like
So
something.
basically, that's the another thing I wanna ask. Like usually, yes, you might put too much fans, but you also have kind of a limitation on per airflow that you can move on the per rack. Airflow that you can move per rack is like how much airflow that you can push into a single rack space in a data center.
But that's limited by noise.
That's limited by noise and also the airflow speed.
Yes.
Yeah, because it creates a lot of back pressure if you increase the speed now because your hot aisles are a certain width, like 2 feet or 3 feet or 4 feet, whatever it is. Now you are limited by that, like, and you have higher back pressure and you limit your airflow also.
But I
Yeah,
think the point of the presentation is that the rear door heat exchanger has an upper bound of 45 kilowatts, and if I start filling this thing full of NVIDIA GPUs, if I had an existing system that's rear door, and I start upgrading my servers that are in there, and I'm using newer GPUs that are in there, and my thermal capacity now is exceeding 50 kilowatts, I need another cooling technology, and a rear door heat exchanger has met its limits. Here's another technology I can use and still not connect to the facility water. I'm still effectively an air-cooled system. And now with a single cabinet width, I can bump my cooling capacity, from 45 kilowatts up to 50 to 60 kilowatts.
Okay.
Yeah.
What you said
If
is
you,
right, definitely. There are multiple other factors that also influence is what I'm trying to tell. That's it.
Rajesh, there is something more you have to take care. If you put the numbers, you put, okay, we have 30 degrees or 25 degrees air temperature before the servers. After the servers, you will have something more, 5 Kelvin more, something like that. You will have 30 degrees.
Basically, if you put approach temperature, you really don't care about the absolute temperature, right?
It's important because at least it's important because you are very limited by the temperature of the air of the data center. If you cannot put the air by 0 degrees Celsius, but neither to 35 degrees Celsius. From the low level of the temperature, are you limited by the energy consumption? Because you will need, as lower as the temperature of the data center, higher is the power consumption of the chillers and so on. Yeah. Or maybe they have no chillers. So something normal is 25 degrees, 30 degrees. But on the other hand, the microchips are limited by technology and you have to set a certain temperature. Let me say 35 degrees, 40 degrees, 45 degrees. But we can start with 35 degrees. So before the rack, you have 25. but the water temperature should be 35. So an approach of 10 Kelvin. In the case of the sidecar, it's right. An approach of 10 Kelvin, you receive the air with 25 degrees. The water should be 35. Perfect. On the rear door, you have something else because the fresh air is 25 degrees, but after the IT gear, you have 30. So if you want to compare the technology, you have to take an approach of 5 Kelvin to deploy the same conditions in which you will cool down the system, you know? So if you take an approach of 5 Kelvin, the cooling capacity will be the half if you compare to 10 Kelvin. So if you compare at the end both systems, the sidecar have a much larger capacity because they have more space, but also because the sidecar is getting fresh air, not air from the servers.
Right.
And this is something to consider as well.
Yeah, and that's something that should be explained in the presentation, but would be reflected in this diagram by the increased cooling capacity of the sidecar versus the rear door heat exchanger.
Yeah. But this is a really important aspect. For if you have air-cooled servers, which is cooled by, I don't know, 30% air-cooled and 70% liquid-cooled, then you increase the temperature of the air before the air go into the reactor. Yeah.
Yeah, what you said is right.
But the only result of that is cooling capacity.
Yeah.
You know, it reduces the cooling capacity of the rear door heat exchanger relative to the sidecar.
Yeah, yes. At the end, this is the result.
Okay. Does this make sense then?
I think so.
Okay. And this could be anything. Like I really don't want to define this. This is something I didn't wanna talk about because that is very new in terms of the technology wise, or like I really don't know.
But the same formula is true. If you can get 50 to 60 kilowatts per cabinet width, the bottom one there is n point something cabinet widths wide. So the cooling capacity should be some fractional number of cabinet widths.
It could be, and at the same time, its efficiency will also be a little bit different from others because now you have one type of radiator or heat exchanger in this, right? Because you are limited by the width on the depth. Now, if the width is not a concern, like they can have literally a single heat exchanger or two heat exchangers that might be of a different width and different depth. That will change the efficiency of the heat exchanger and also overall solution.
Yeah.
Does that make sense?
Yeah. Now, if the bottom one were 2 cabinets wide, the bottom one would probably have a cooling capacity that is more than twice what a single wide is, just because of the design efficiencies that you'd get with a single large heat exchanger versus 2 smaller ones.
Yes, it could be. Yes, the efficiency is higher. That's why like there could be maybe 10% more cooling capacity in
So,
that way.
So maybe instead of showing the bottom one being almost 3 cabinets wide, as you make the bottom one 2 cabinets wide. So change the box so it is the same size as the double one that's above it.
Yeah, this one I didn't want to define as the same. I wanted to define it as how much hour they want. Like this could be 3, this could be 5, this could be 10, this could be 20. This
But I,
doesn't matter.
but I think the point of a single wider one is more efficient for cooling than 2 single cabinet wide ones is kind of lost unless you're calling this 3 cabinets wide. So I think
Yes.
as a design point for selling this technology, if you made this one the same width as a double one, and in the formula on there, your X would be X times 1.2 or something like that. You need to somehow add into this diagram the idea that a single double wide one has more than twice the cooling of 2 single wide ones.
I see. I see what you're saying. So in that sense, I could say here, multiplied by
Is it 10% or
1.2,
something like that?
something like that.
20%? Yeah, right.
Yeah. I want to say 5 to 10%. Actually, 10% is a very, very good, a generous one, because so now you are considering even the gaps between these two are smudged. So now you are not giving any rack space between these two racks, and also you are trying to fill that with a heat exchanger, something like that.
Yep, and you're also getting better airflow because the airflow is straighter through the wider cabinet than it is through the narrower cabinet.
Yes, yes. So you have multiple again, like efficiency features into this. Now you can use bigger fans than whatever you are using in this. So there are a little bit more multiple advantages. That's why, like, I think 1.2 is a good justification for
Yep.
this.
And the other point on this is that no matter what your IT cooling rack requirements are, you can just put a bigger and a bigger sidecar in there to cover it. So when NVIDIA comes out with their kilowatt GPUs, there's a solution for it.
Yes, that's the idea. Yeah. Now you have multiple solutions where you can have multiple sidecars put for a single one, or you can have a very big, wide sidecar. But in that, like that's the one other thing that I want to say is what is the sidecar dimensions could be, this could be uh, like defining what could be fixed, what is not fixed. So for example, if I take a small one single sidecar, I'll take from this actually. Now in this you have the depth, the width, and the height. You cannot change the depth now because the depth is defined by the cold aisle and hot aisle. So the depth has to be in very very close relationship, like with the IT gear, so that you don't interfere with any other hardware, um, because the data center was initially designed for IT gear itself, the rack itself.
Yeah, in some cases, you can go taller.
Yeah, the tall, yes, I think you can go a little bit of taller, based on how high or like is your power rails, how is your network rails or network, the trays that run on the top, so on and so forth. So there are limitations on that side also, um, on how high you can go, because you don't want so close to those power rails and network rails, right? And in terms of depth, width is something you can play with. You can have the width as a single sidecar to be consistent with the design, and you don't have to form a new logistical infrastructure to move the rack. That's one. Or you form a gigantic sidecar that you install it once and then that's it. Like you treat that as another data center equipment, not the rack equipment anymore.
But the single unit, very wide sidecar has lots of design features in it that make it more efficient than multiple single wides.
Yes.
And cost efficiencies, because you'd have a single RPU in it instead of two with the two singles.
Yeah, so the components we defined here, the hot swappable critical components, non-critical components, single point failures, so these remain the same even for that, if you
Right,
ask
but
me.
but a single double wide one has, you know, almost half the components in it than two single wides, because you'd run RPU in a double wide sidecar.
No, not necessarily. You can just upgrade everything. So for example, here in a single sidecar, um, you can use maybe pumps would be smaller because you are very constrained and you also want to have n+1 redundancy. So now you constrain yourself on the size of the pump, the height of the pump, and everything. But in this, you don't have that constraint now.
Right,
You can have a
but the
sidecar pump
but
on the side.
the two single wide sidecar is going to have 4 pumps in it.
It could have 4 or more, or even like even 3 should work. 3 could work. Like if you go to, let's say, an AC pump instead of a DC pump, now
But if you did a double wide sidecar, you'd probably put 2 pumps in it,
uh,
2
even
larger pumps.
so even a single sidecar will have right now, I think, 3 pumps. At least 3 pumps, yes, to have n+1 redundancy.
And ours have 2.
Yeah, the designs change from I think company to company. I have seen
Yeah.
3. But in a double-wided one, now you will have same 3 or 4 with higher capacity instead of the lower capacity flow rate. So that's the difference. Like your components would change, but they're similar components. Like they're still gonna be using pumps, but with a higher rating, higher pressure drop, and higher. You can reduce the number of components. So when you reduce the number of components, your failure rates will change, and also your efficiencies will change.
But that's I think one of the points of the same slide is that a single sidecar and a wide sidecar would have similar part counts, and the 2 single wides would potentially have twice the part count, so that a single double wide sidecar would probably have a better reliability rating than 2 single wide sidecars.
Yeah, that could be right. That could be. It all depends upon the designer.
Yep.
Um, yeah, the next one I want to create a drawing actually, where we define the, like as I said, the depth and the uh, height and width. So in that sense, that also comes under data center limitations, right? What could be the depth, what could be the height, and what could be the so for example, this. So is there any dimensions that we can fix in this, or like should say, hey, this is height, depth, and width, and height should be of this much. It cannot change because of the data center limitations for this.
Since this is OCP we're working with here, I would expect that the sidecar would have similar dimensions to a OCP v3 rack.
That's my assumption too, to be honest. Yeah. But is there any other dimensions that we need to also consider, like in terms of height, like could it be higher than OCP or a rack config, or
Yeah, we just discussed that, but if you could present that on there, that you could squeeze a little bit more cooling capacity by increasing the height of it, but you already went through the list of limitations on there as to where the bus bars are, where the network wiring and things like that are, that you could get, a small amount of increase in cooling by keeping the width the same and increasing the height of it. But if you need a significant increase in the cooling, then the only dimension that you really can change would be the width.
Yes, width would be the only dimension. That would be same as IT rack. Three. Should I leave it at like OR v3? Sorry, IT rack.
Yeah, I would do the depth and the height as OpenRack v3. And when you're presenting it, say that you could squeeze a little bit of height out of this.
Gotcha. Apart from the height in the room, is there any other limiting factor that comes into mind when it comes to height, like the doors that are used for entering the data hall, or the containers that are being shipped? Like, is there any other limitations that I overseen?
Well, doors in the data center usually aren't a limit because they make rack carts that tip the cabinet down to like a 45-degree angle, so you can get it through big cabinets through little doors.
Okay.
I think, like you said earlier, the limitation on the height is going to be bus bars and network wiring.
Gotcha. Okay. Yeah. Okay. I'm gonna create another slide over here to for this dimension comparison. Yeah. I might have to create a little bit more better picture or for this, I guess. Or that sounds good. Okay, I think we are at time. I'm gonna add that slide, but in the next 3 days, by next week, I'll also try to see how much of I can format this into a document versus a bullet point. I would appreciate any help from you folks to if you want to add or edit any section, please feel free to do that so that it's gonna be quicker. And I'll add as much as I can.
Okay.
Yeah.
Next meeting is next week.
Yeah. For now, we haven't gotten any progress on this, so this I think for next month also we might need some at least for until OCP. I want to keep this as a weekly for now, unless until there is a clash between rear door heat exchanger calls and this.
Yeah.
When is your rear door heat exchanger call on?
I don't know. I think end of the month of each month should be this week, or but I am not sure. I don't know.
Okay, I'll talk to Jabari and then see like maybe cancel the overlap meeting for the next one.
Okay.
Yeah. Thank you.
Okay. Thank you very much.
Thank you.
Bye bye.
Bye.
Bye-bye.